let's go up a level just for a second.
Okay, let's get started.
What have we built so far? Simple objects, the idea of iteration, for and while loops is a way of doing particular kinds of computations, reusing the same piece of code over and over again. And now we've introduced the idea of functions as a way of capturing that code. That puts us in a position to introduce another really big idea in computer science, and that's the notion of recursion. I'm going to show you an example of recursion in a second, but let me give you the sense of what recursion is about. Recursion is going to be a nice way to design solutions to problems by breaking it up into pieces that I can reuse. Divide and conquer or decrease and conquer are words I'm going to use around here. And it's in particular a programming technique where inside of the function, it calls itself. So I'm going to define a function, say f. And inside the body of the function, I'm actually going to call f. Now this is the kind of thing that in high school geometry class you could get into trouble, right? You don't define something in terms of itself. But in recursion, as long as we don't set up an infinite loop, we don't call it infinite numbers of times, we're fine. And so we're going to see in recursion that as long as we have one or more base cases that are really easy to solve and can be solved directly, then I can solve a problem by reducing it to a solution to a simpler...
I'm just going to write down my notes. Base cases. And we'll solve the same problem.
version of the same problem until I get down to a simple base case. That notion of recursion is going to nicely amplify iteration. It's going to give us a much more simple way of thinking about how to break problems up into simple pieces. And so we're going to spend the next portion of this lecture just looking at different ways of using recursion. If you think about iterative algorithms to set the state for recursion, what do we have? They're basically looping constructs. And they are captured by the idea of having a set of state variables that update each time through the loop. So I've got a while loop or a for loop. In the case of a while loop, we talked about setting up the variable outside the loop, inside the loop changing it, usually decreasing it, until I got down to a state where I'm done, and then returning a value. That's what an iterative algorithm does. So here's a simple example to think about that. Suppose I wanted to do integer multiplication. And yeah, I know that already happens in Python, but I want to use it as an example. I could think about multiplying a by b as the same thing as adding a to itself b times. So it's really, if you like, a plus, I've got b of those. That's the same thing as a times b. Iteratively, I would solve this by saying, I'm going to capture the state of the computation with an iteration variable. Let's call it I. I'm going to start it off at b because I got b additions to do. And a current state of the computation. I'm going to call it result. And I'll start that off at 0. And then my iteration is to simply, at each stage, do one more addition and reduce that variable by 1, that iteration variable by 1. And down here at the bottom is a function to do that. Multiplication iterative takes in two parameters, a and b. It sets result when I call it to 0, and then it runs the iteration I'd expect, that little loop right here. that says as long as b is bigger than 0, I'm going to change result by
Value. Computation. Results. Fancy words for results. I get results. Results. Plus A. Yeah, okay.
adding a to it. I'm going to reduce b by 1, and I'm going to keep doing that until b gets down to 0, in which case I'm going to return the result. Cool. Nice iterative way of trying to make that happen. There's the iteration. There's how I'm changing the computation. There's where I'm changing the iteration variable. And when I'm done, I'm simply going to return the result. Okay. I'm not going to run it. I encourage you to try it yourself, but you'll see that it actually does the multiplication I'd expect. With that in mind, now let's look at a recursive solution to this problem. And here's a way about thinking about this idea of doing successive additions to compute multiplication recursively. Again, a times b is adding a to itself b times. But I could think of that as saying that's the same as adding a to itself b minus 1 times. Okay, you say, that sounds like semantics. It is, but it's an important point. Because what's this? That's just a multiplied by b minus 1. Ooh, that's cool. Because now I've taken a problem and I've reduced it to a simpler version of the same problem, plus an operation I know how to do. Okay, what's a times b minus 1? Oh, I know how to do that. That is just a plus a times b minus 2. I could do exactly the same reduction. And I could keep unwinding this computation. I need to stop somewhere. I could keep unwinding this computation until I get down to a base case, something that I know how to do. And what's the base case? When b is equal to 1, the answer is just a. And boy, that's nice, because there's a recursive implementation of multiplication. Inside the body, it says, if b is equal to 1.
Wow. And keep going all the way to the base case. And the base case is if b equals 1. So here, base case is when b equals 1, a times b equals a. Okay.
1, that's my base case. Just return a. Otherwise, return whatever.
Oh, and I want to write this down too. Let's see. If b is equal to a, return a, else return a plus multiplication a comma b minus 1.
I get by adding a to doing the same thing, but on a slightly smaller problem, multiplying a times b minus 1. And that will again call itself until we get unwound down to the level that we want to get to. There's the recursive step. And that's a standard form for a recursive function and is a really elegant way of thinking about how to solve this problem.
Oh, wait 1 second. This is the base case here. And this is the recursion. Okay, first page of notes done.
I could do the same thing. Let's think about computing factorial. Factorial, written mathematically as n followed by an exclamation point, is the product of n times n minus 1 times n minus 2 all the way down to 1, where n is a positive integer. If I wanted to solve this problem, I could say, so what values, or for what values do I actually know factorial? And that's easy. If n is 1, factorial of 1 is just 1. There's my base case and the value I want to return. How would I return it? Well, just as I did with the multiplication case, n factorial is the same as multiplying n by n minus 1 factorial. So there's the recursive step. And I've just written the body of code for something that would be a definition for factorial or fact. What you're seeing here is a pattern, and this is the idea of a recursive function. Break it down into a smaller version of the same problem, plus some operations I want to do, and figure out when can I stop breaking it down into smaller versions of the same problem because I know how to compute it directly. In the case of factorial, when I get down to a factorial of 1. With that in mind, let's deal with something that may be puzzling you, which is how in the world does the computer know when to stop unwinding this? And how does the computer know which versions of the function, of the parameters to the function to use? I'm calling fact of n. How does it know which version of n to use? We've already kind of seen it, but let's walk it through. So here's my definition of fact. Fact of n is if n is equal to 1, return 1. Otherwise, return n times fact of.
Okay, this is an example, so I'm just going to write this down. Define fact n if n is equal to turn 1, else turn and fact n minus 1. And then we test print fact 4.
To n minus 1. Then I'm going to call it on a value of 4, and I want to print out the result of that. I'm going to do this reasonably quickly because you've seen these pieces before, but let's look at what happens. When I define fact in that global scope, I create a binding of fact to some code. Hasn't been run yet, and now I'm ready to run it by actually calling it on print of fact 4. Okay, here we go. I've got to call fact of 4. Fact creates a new scope inside of which n is bound to 4. And relative to that, it's going to evaluate the body of the procedure. It says, is n equal to 1? No, it's equal to 4 here. So I go to the else clause, which says return n times fact of n minus 1. Aha, I got to call fact again. I know I want to return fact, or 4 times fact of 3. That's the value of n minus 1, but I got to call fact. Great. It creates a new frame, inside of which the formal parameter, n up here, is bound to 3. And relative to that, it does exactly the same thing. So I'm now going to go faster. Is 3 equal to 1? No. So I'm going to
Global scope. Facts, some code. And that's where we put the print fact 4. And then it's going to go to the next one, which is the fact scope. Fact scope. And equals 4. And then that would make this turn 4 times fact 3. And then we say fact scope n equals 3. N equals 1. I'm just going to turn 4 times.
return 3 times call.
Ooh, 3 times. Sorry, 3 times fact 2. Turn 2 times fact 1. And then this is just return 1. Right? Let's see.
Calling fact on n minus 1, which is 2. That calls a new frame. There's the binding for n. n still not equal to 1. I'm going to again go to the return clause or the else clause that says return 2, which is the value of n times fact of n minus 1, which is 1. And that calls one more frame. And aren't you glad I didn't do fact of 64? Almost done. In that frame, I now say, is n equal to 1? Great, it is. And so in that case, I know that's the expression I want to call. And it says, return 1. Where does that go? I'm returning 1 to the person who asked for it. And that was that call to fact. That's great, because now that expression says return 2 times 1, the value returned by that call to fact. And who asked for that? Right there. That reduces to return 3 times 2, which reduces that one to return 4 times 6, which prints out 24. And I'm done. So you can see the computer with these scopes, nested scopes, these nested frames, nicely knows exactly where to get values in order to do the computation. And therefore, the computer knows to stop at the right time. I've just said that. I'm simply going to put the slide up so you can see it. Each recursive call creates its own scope. Bindings of variables in a scope are not changed by the recursive call, and the flow of control passes back to the previous scope because that was the person who asked for that function call as we did it. And therefore, I'm going to be able to use exactly the same variable name. I need to, because that's the formal parameter of the function, but it's always done in a different scope, and therefore it's always clear which version I'm using when I'm calling the body of the procedure. This leaves us then with this nice comparison between iteration and recursion. Both of these pieces of code do exactly the same thing in terms of what they compute. How they do it is done differently. I'll let you decide your own style. Personally, I like recursion better. I think it's more intuitive. I don't have to remember to set up a parameter variable before I start things. I don't have to worry about dealing with all those pieces. I can make them a little different. In this case, I've changed it slightly to use range rather than setting up the iteration variable. But I personally find the right-hand side easier to look at because I can easily see where the recursive call is. From the programmer's point of view, recursion may be more efficient. From the computer's point of view, it may not be as efficient, and we'll see that. But basically the idea is each of these things does the same thing. You get to decide which one you want to use.
Okay. Going on to the next. All right. What happened to our music? Is it just too quiet? Did it somehow get turned off? Weird. Why can't I adjust that? Super weird. How do I turn up the volume? Drag to adjust the volume, but it's not letting me drag. Super weird. Okay, let's reload this page. I hope that works. Okay. All right, let's do this. Write an iterative function. Calculates the exponential base by simply using successive multiplication. Okay. Okay, so we can't use to the power of. Okay, iterative power base takes base an exponent. By simply using successive multiplication. So what happens? When exponent is equal to 0, right? When exp is 0, what do we get? Return base? Oops. Hitting too many buttons. Okay, let's look at our calculator here. I want scientific. 5 to 0 is 1. Okay, so when exponent is 0, how do we set this up again? What's happening again? How do we do this? If, there we go. Yeah, that's right. If, oh my, if exp equals 0, return base. No, return 1. Right? Yeah. Else, return base times, no, base plus, it's not plus, it's times, right? Okay, so we'll call it self. Return base times iter power base minus 1. Base will stay the same. Exponent decreases. Is this going to be right? Let's see. I can put it into Spider and see what happens. Let's open a new one here. Yeah, sure. So this one we're gonna save as what? Nothing for now. Let's just put this in here and see what it does. If it does what we think it should do. Make sure we have an extra like space in there. Gotta have your white space. Okay. Let's run this and see what happens. What are we gonna call it? Calculating powers by iteration. I don't think that's right. I think I did it as recursion. Incorrect. Iterative, not recursive. That's the problem. Okay. So iterative was exp minus equals 1. And then when exp equals 0, okay. Is this a while loop? So while exponent is greater than or equal to 0, greater than 0. We do base. Times how are we going to do this? I feel like we should know how to do this. Just reading over all my notes. While exponent is greater than 0, we're going to return base times base. Is that right? This is so cruel. They're like, oh, hey, you just learned recursion, but we're going to make your questions be on all the stuff you were supposed to know before. Let's see. It just shows that obviously I don't know what I'm doing. If here we go. Okay. Let's say if exponent equals 0, return base. While exponent greater than 0, return base times whatever, and then we're going to reduce that one, right? Oops. I think this should be an else statement. Else return base, right? That works. Now, what is powers? Powers are mathematically, what does it look like? It's the base times the exponent, which is really base times the base, the number of times there are exponents. So it's base times base exponent minus 1. That's what powers should look like, I think. But that's still doing recursion because I'm asking it to do it again. Return base times base times 1 minus 1. That make the exponent 1 smaller. Let's give it a try, see what happens. Still incorrect. Let's see. Ah, okay. So it does need to go first. And we don't return base, we return 1. Which one was the float? The base. Can we make it integers? It returns an integer or a float, so I can't make them integers. Well, we fixed that one, right? When exponent is 0, it returns a 1. So we fixed that one. But all of this line 11 is wrong. Float object is not callable. And the float is the base. How about results equals this? And first we need to say result equals 0. And then results plus equals result. Is that going to work? Let's call this step, just so it makes sense. So then result is going to be plus or equal to the step there. Oh, still not right. Oh, I feel like we're getting closer. All right, the first one worked. Still giving me a float object is not callable. But if I make this an integer, then that's going to be a problem because it's going to take off the decimal points. We want it to happen. What are we going to do to resolve this? What can we do? Let's see if they got any hints. Make sure you don't call the function in the console in case you have done so in Spider to check your answer. .62 out of 5 points. Come on now. Can we say like yes? Okay, let's look at it in Spider again and see if we can run some test trials. So let's try two to the power of 3, we get 8. Let's see what happens. Okay, so we get the right answer. But I might still not be happy. Let's do 2.5. Interesting. Oh, that's because I'm not using this. Oh my god. Hard eye roll first rolling right there. This was the recursion, and of course it worked. Okay, it's still giving me the float cop. Okay. Can I do like while how do we want to set this up? We want these to be eyes, right? So then we want that gonna work? No, it's the same thing. Results plus equals. What are we saying here? Result plus equals what? that doesn't work. Let's make I equal to the. Why can't I call a float? I'm gonna get this one way or another. It's not callable. Getting closer. This will work itself out because it will be negative if it's multiplied an odd number of times, and positive if it's multiplied an even number of times, which is exactly what would happen in the powers. So we don't need to worry about like absolutes or anything like that. So far, anything that works with zeros, anything that has a 0 as the exponent works. So we know that the else here works. What if instead of while we say if? No, we keep it as well. We've spent a while on this. Let's see. I wish they had like hints. I think that would be good. Let's keep saying for a for loop. So for I no for Error. Okay, that's not valid for a 4. Let's see the answer. Result equals 1 while exponent greater than or equal to 0. Result times equals base. That's why it has to be 1. I see, because they're doing it like this. Okay, so I'm going to write it in Spider now. Times equals base. Yeah. And then we decrement the exponents by 1. And then return result. Because we don't need the other step because it's 1 regardless. Yeah. I get it. Because that's what we were doing, was just multiplying it by itself. That many times, however many exponents there were. Man, I feel like I should have gotten that. Okay, now we do recursion, right? If 0, return 1, else return base times base exp minus 1. Return result. Just set result outside. Or do we... Is that right? What should your base case be? Okay. Smallest value exponent can be 0, and that equals to 1. Yeah. Oh, but here we return Yeah. If you're getting an error stating that your code should be recursive when you already make a call to recur power, check your indentation. Specifically, common mistake is that your function and docstring do not start at the same indentation level. Okay. We have to call it inside, right? Return n times recur power base comma exponent 1. Is that right? I don't know how I feel about that. Yeah, looks like it. Nice. Okay. I got that one correct right away, so that feels nice. Had the discussion, and let's go to the next one. What do we have next? More videos. 2 videos in a row now. More notes.
We just saw an example where we walked through carefully the execution or the invocation of a function call, a factorial, in order to see how the different scope frames were created and help us sort of decide that in fact it will stop when it reaches a base case and return a value. But when I start trying to design code, I have to think about the same thing. How do I set it up so that I know it's actually going to stop? How do we know a recursive code is going to work? In the case of an iteration, we know that by making sure that we've got a loop invariant that changes as we go through it in order to make sure that we actually get down to a place where we hit the end test. So mult_iter terminates because b is initially positive and it decreases by 1 each time through. I've set that up by making sure I change it by 1. And so I know eventually it's got to get down to a place where it's less than 1, which is going to trigger that end clause. And I can use that to deduce that I've written code that is in fact going to terminate if I give it an appropriate set of values. What about the recursive version? So as I said, mult is called with b1, and then it has no recursive call, and it stops. But how do I know that it stops in general? Well, if I call mult where b is greater than 1, it makes a recursive call with a smaller version of b. And so again, I know that eventually it must reach a call where b is equal to 1. This tells me that when I write a recursive version of a function, I need to make sure that I'm changing the parameter, in this case this value, so that I'm going to get down to that test case. That's nice. But there's another way in which, in fact, I could reason about my code to decide, is it going to, in fact, terminate, or is it going to get into an infinite loop because it's going to recursively call itself over and over again? And to do that, we can use, as a little sidebar, a nice little mathematical tool called mathematical induction. Here's the idea behind induction. If I want to prove a statement that is indexed on integers, is it?
All right, hold on. Take notes. For all values of n. Prove it's true when n is the smallest value. And then prove that it is true for an arbitrary value of n one can show that it must be true for n plus 1. Okay. Arbitrary value. Okay.
That is, it's a statement that is applied to a set of integers. If I want to prove that statement is true for all values of some parameter n, I just need to prove that it's true when n has its smallest value. For example, n is equal to 0 or 1. And then I need to prove that if it is true on an arbitrary value of n, I can also then show that it must be true for n plus 1. And with that, I can then essentially deduce mathematically that it's true for all values of n. Let me show you a little mathematical example of this. The sum of the integers for 0 up to n, I claim is n times n plus 1 divided by 2. If n is 1, it says 1 times 2 over 2 is 1. If it's 2, 1 plus 2 is 3, and 2 times 3 divided by 2 is 3. You get the idea. How would I prove this is actually a true statement? Well, the proof says, take the simplest case. If n is equal to 0, what do I have? Then the left-hand side is just 0, and the right-hand side is 0 times 1 divided by 2, which is just 0, so it's true. To prove it in general, I simply assume it's true for some values, let's call it k. And then I need to show that it's true for k plus 1. So I need to show that this statement is true. Oh, but that's nice, because the left-hand side, I know that it's true for that. I just assume that. I know that in that case, that is k times k plus 1 divided by 2. So the left-hand side is simply that, by that assumption. And if I do just a little bit of algebra, I can show that that is, in fact, the same as this. And I'm done. Having proved it, assuming k, therefore, it's true for k plus 1, I can now say it's true for all values of n. So this formula is always true. What does that have to do with code? Well, I can do the same thing. Here, with my case of a recursive call to mult, I need to do the following. I need to show the base case is true. Will this return the right answer when b is equal to 1? Yep. Now, what about in the recursive case? I'm going to assume that my code does the right thing for smaller versions of the problem, meaning that I'm going to assume that mult returns the right answer. And in that case, I can then say on this piece of code, if it does the right thing, then this return does the right thing, because it's simply an addition. So in that case, I know it returns the right answer for a problem of size b. And by mathematical induction, my code will always do the right thing for appropriate values of a and b. Thus, induction tells me I've got code that works.
Okay, on to the next one. Let's see what this is about.
We've seen some simple examples of recursion. Factorial, doing multiplication by doing recursive addition. These are nice places to start. But recursion is actually really a powerful tool, and I want to show you a very different way of thinking about recursion on a problem that's otherwise hard to solve if you don't think about it recursively. And this is to take a classic problem called the Towers of Hanoi. The story is that somewhere in a temple in Hanoi, there are 3 tall spikes, on which there are initially 64 discs of different sizes, all stacked together in decreasing order, with the largest at the bottom going all the way up to having the smallest at the top. And the goal of the priests in this temple is to move the entire stack from one spike to another one, moving one disc at a time, but with the property that they can never have a larger disc covering up a smaller disc. And there's a little animation you may be watching at the bottom here that's showing an example of that with a stack of size 3. We want to figure out, how would I write a program to tell the priests exactly how to move those discs so that they can move all 64 from one spike to the other. And I'm going to do a little demo to show that to you. So I want to demonstrate for you how to solve Towers of Hanoi, and especially how to use recursive thinking to do that. But to begin with, I'm simply going to show you solutions to Towers of Hanoi and see if you could figure out how to write code to describe the set of moves that would solve it. Let's start with the easiest case. I have a stack of size 1. Moving it is easy. I just move the disk. If I have a stack of size 2, I know I've got to move the smaller disk to the spare place while I move the bottom one, and then move it over. Pretty straightforward. If I want to move a stack of size 3, it takes a little more work, because I got to move the top disk. I got to be careful not to cover up a smaller disk with a larger one. But once I've cleared the bottom disk, I can move it, and again move the top disk to the spare one so that I move the entire thing without covering up a smaller disk with a larger disk. Also pretty easy. But what about a stack of size 4? It takes a little more thinking because I have to really be careful here that I'm not accidentally covering things up, and it takes a lot more work to in fact expose that bottom disc, which I'm now ready to move. Now I got to get all of those back over again without covering a smaller disc with a larger one, and so that allows me basically to make that set of moves to get to that point. Great. Easy to write code to do this, right? Probably not. But if I think about it recursively, it's really easy. So what does that mean? I want to move a stack of n disks. And recursively, I would say, if I already knew how to move a smaller stack, what's my solution? Oh, that's easy. Move a slightly smaller stack to the spare disk. Now I can move the bottom disk and move that stack to the target. And what does it mean to move that stack to the target? Move a slightly smaller stack to the spare disk, move the bottom one, and move that stack. And I'll just keep unwinding that until I'm just moving single disks. Recursively, this is easy to see, and that leads to a very natural implementation. Okay, what you saw in that demo is that it's going to be hard, even if you watch things like moving a stack of 3 or a stack of 4, how would you write the code to do it? And then what you saw is if I think about it recursively, it's actually really easy. Because recursively, what do? I solve a smaller problem. Move a stack of size n-1 onto the spare disk. Then I've got just one disk left on the bottom of it. I move that one, it's a simpler problem. And then I move that stack that I temporarily moved to the other side back onto the place I'm going to. Recursively, this is really easy to see. And so even though this looked like a very hard problem, it's very easy to write code to do it. And so there is, in fact, a little set of code that says I got a
Okay.
function that simply says print an individual move from the from stack to the to stack. And then here, notice what I've got. I've got a test for a base case. If I've got just a stack of size 1, I'm just going to print the move to take it from to 2. Otherwise, I actually now have to solve 2 recursive problems. So it's a little bit different. I'm going to move a smaller stack from the from to the spare spot. Having done that, I'm going to move the simple case to the place I'm trying to go to. And then I got to move another, that smaller size stack from the spare over to the 2 spot. But the code itself is really straightforward. And if in fact I go and run this on a stack of size 4, it gives me very nicely all of the moves I want to do to move that stack over. What I want you to see here are 2 things. 1, I can have multiple recursive calls inside of the function body. It's perfectly fine. And 2, this is a problem that I suggest is really hard to solve iteratively, but elegantly easy to solve recursively. And I want you to think about that notion of break it down into a smaller version of the same problem, assume that can be solved, build your solution with that and other simple operations, and let the recursion then unwind it to get to the solution that you want.
Okay. Let's do some more problems. Okay. Greatest common divisor of 2 positive integers is the largest share of the divides integer. iterative function that implements this idea. Begin with the test value equal to the smaller of the two input arguments and iteratively reduce this test value by 1 until you reach either a case where the test divides both A and B without remainder, or you reach 1. Okay. Okay, so what are we saying we're doing? We're taking, I think it needs to be a couple of steps, right? Because first we need to test if it is. So we'll say else return B divided by A, and B modulo A let's see. That's going to tell us if there's a remainder. Else if return A. Else return GCD iter A minus 1 and B, right? Let's give that a shot. What does it look like it's gonna do? Let's put these in here and then we're gonna try some over in Spider, see how it is. Let's do a new one. Greatest common denominator. New. Print. Greatest common denominator. Okay. Oops, I printed the wrong thing. Print GCD iter AB. Another. There we go. Happy? 4. Okay, let's try one that isn't so good. Let's try 12. Give us 8. Okay. But that's not right because 8 does not go into 12 as well. If b modulo a is 0 and a modulo a is 1, or no, is 0 as well, modulo, not dividing. Okay, so we need that. So let's see. And a modulo a equals 0. Let's try that. Double equals. Still giving 8. That's not possible. It's not quite right. I'm not quite doing the math right here because this needs to be. This is right, but it shouldn't be 8. It should still be 4 because 8 doesn't go into 12 evenly. It does go into 16 evenly, and the problem here is I'm saying A is subtracting by 1, but it's not the original A. Getting close. If b modulo a is 0 and a modulo a is 0, return A. And then we want to do A minus 1. Right? Because this should go. What's wrong with this right now is that it's subtracting, and then when it gets to 1 that's also in here, it's saying yes because it's doing 12, 16 divided by 12. No, that's not it, so it kicks it out. And then it reduces this one and it says 11 into 16. No, kicks it out. But this one is always true because it keeps saying this one minus 1. So this will always be true, and we don't want it to be true. We want the original A. I don't quite have this right. What's the simplest base? Maybe I'm not thinking of the simplest base. The base case. Is the base case if A equals 1? return 1. Or is the base case if A equals B? But we don't always know that A will get to B. It's got to be if A equals 1. Begin with a test value equal to the smaller of the two input arguments. So we'll start with this. If B modulo A is 0 and A, let's start with this. Four, okay. So we're saying if B, what is the remainder of B divided by A? So if the remainder of B divided by A is equal to 0 and the remainder of A divided by A equals 0, return A. But I don't think we need this one here because that one will always be true. So there's no point in adding that there. So first we would just test, right? That's always the first, that's the base case, right? If B divided by A has no remainder, we return A. Else we iterate and return that. Incorrect. What's my error? Let's see. Iterative, not recursive. So while A okay, let's save this one because this looks like it could be the next answer of being recursive. Let's see. Notepad, please. Thank you. Okay. While A greater than 1, and what are we going to do if A, oops, there we go, and say if A equals 1, then we return A. So while A is greater than 1, we return A. We know that it will be less than 1, and we know that it won't be So while a is greater than 1, if the remainder of b divided by a is 0, we return a. Else we return the same function again, with a being less than 1 and b remaining the same. And then when we go again and a is equal to 1, like so we say 2, and then we'll subtract 1, it'll be 1, and it won't be greater than 1, so it'll just be else and return a. Maybe? Perhaps? Let's give it a try. No, it's still not happy. Looking at my notes, looking at my notes. Should probably look at some hints, I guess. Did we copy this? Copy. Paste. Let's try GCD. What are we going to do? 4 and 16. We'll see if we get a good answer. And we're going to call this iterative. Oh, that's why, because it's calling itself. That's why it's saying it's recursive. So it can't be like this. So what are we returning instead? We're going to return a. We're going to decrement it down. Let's try this again. So close, but we got 1 point out of 5. While a is greater than 1. I don't even think I need this because once we get to 1, this is going to be true anyway, right? I think so. So as long as the remainder of b divided by a is 0, we'll return a. But I don't think, this still doesn't address, it's giving me the output of the greatest common denominator of 12 and 16 being 8, which is not the case. I feel like we need to store a someplace and then decrement down from that. That's what I feel like. So that only takes care of that case, but it doesn't run the test. We need a secondary test where it also tests the original A. So instead of saying, okay, we need something else. So what do we need? How are we going to do this? We need to keep the original A, but also decrement A, and then compare it to its original self. Okay. So why don't we say maybe we could make it GS or GCD, greatest common denominator, equal to A. And then instead of B divided by A, we'd say B divided by the greatest common denominator, while greatest common denominator is greater than 0. So let's see if we can do that. I don't know, because that's what's going on. We're decrementing the A, and then of course that's always going to be its own common denominator because we don't have the original one. We do with recursion, but I'm not sure with iteration where that goes, because so we also need to check A. We need to keep the original A. And when we decrement it, we'll save it as greatest common denominator. So originally, while A is greater than or equal to 1, greatest common denominator equals A. If B divided by that greatest common denominator equals 0, we return the greatest common denominator. Else, greatest common denominator will get decremented by 1. And A modulo greatest common denominator equal to 0. Let's see. Still incorrect. while greatest common denominator is greater than or equal to 1. This is going to set it every time, and that's not what we want. So that's not going to work either. And this needs to be outside the loop. Does it set it equal to A every time? I don't know. It will, because no, we're saying it's equal to A, and then while this is greater than 1, we do this. And then once it's equal to 1, what do we do? Else we'll return 1, right? 2, 3, 4. Didn't we say we didn't need that because once GCD equals 1, then this would be true and it would return the GCD as 1? Okay, let's try this. This is greatest common denominator recursion. And let's get a new one, and this is going to be paste. Greatest common denominator iteration. Okay. Or 16. Let's try that one first. 4. Okay. Let's try 12 and 16. That was our next one that was giving us problems. 4. Okay. Let's try 3. Oops. Damn it. Damn it. 1. Okay. Let's try this. Okay, and is that the same that's over here? Yes. Let's try it again. Yes! Oh my god, we did it ourselves! Yes, 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 yes. I feel like we're getting this. Making progress. Okay, next. Okay, so we're going to use greatest common denominator recursive, and we're going to use Euclid. Math tricks. Suppose that A and B are two positive integers. If B equals 0, then the answer is A. Otherwise, it's the same as B modulo AB. Okay. This function takes two positive integers and returns one integer. Okay. So recursion, we're going to say if B equals 0, oops. No! Okay, there we go. If B equals 0, return A. Else, return GCD, recur B, comma, A modulo B. Oops, A modulo B. Let's try this. Let's see what this is. Okay, let's see. Okay, this is almost like an epsilon one that we looked at before, because what it's saying we need to do is okay, so we have G, C, D, A, and B, such that we want to write a code that subtracts multiples of B from A until A less than or equal to B. One second, I'll be right back. Just a few more minutes. Okay, let's try this again. So the hint that was given for us was this Euclidean algorithm that finds the greatest common denominator of two integers, positive integers. Oh, that's a nice start stream screen. 1 second. Yeah. So it proceeds in a way that each step is the output of the step before it. K is counting the steps of the algorithm starting with 0. We can see this kind of, they put a, here we go. So this would be it here. So a worked example. Q1 on quotient and remainder. Okay, so each step, so not the base case, but I guess that is the base case when the step is 0. So an R2, when R2 is 0, that's when the algorithm ends. So that's the thing that needs to be decremented. Were they playing? Let's see, A, B. So that's what they're doing. They're doing an initial division and then the next one, correct? So the initial, yes. So I see. So it's A, B, and then the next one is G, C, D, A, B, and then the next one is G, C, D, B, R sub 0, and the next one's G, C, D, R sub 0, R sub 1, all the way until we get to G, C, D, R, n minus 2, R, n minus 1. Which is equal to R sub n minus 1. I'm just going to put that in there. I don't think, we'll see. I don't know anything right now. Okay. This was the hint that was given to us from the exercise here, which was see this website for an example of Euclid's algorithm being used to find the greatest common denominator, because we're going to write this function. Okay, and what makes it recursive is that it sets something, this is the case, and then the recursion calls itself until this case is true. But this isn't even... because it's the remainders. I see. Okay, so that gets us this portion here, because A modulo B gives the remainder of A divided by B. And then the very next one is whatever was in the B position over into the A position. And if B equals 0, return A, so we have that. Otherwise, return this, but we need to be somehow reducing B to 0. We have to decrement it somehow. A modulo B equals 0. Return A modulo B. Right, because how else does B get to 0? Okay. I'm gonna figure this out, unless anybody happens to know. If you do, please explain this to me in a way I can understand. Okay. So this is initially saying that we do a division of A modulo B? No. want A divided by B, but without Q equals 2. So, example. And we're looking for this, right? Quotient of n. Hmm. Okay. Find quotient and remainder that satisfy the equation. RK, so 2, so number of steps minus 2 equals quotient of that step. And then the remainder from that to make that true. Okay. And that have RK less than RK minus 1. RK less than RK minus 1. Okay, so that's one of the things we need to say is RK less than RK minus 1, because that's where we get to our stopping point. Okay, this is the procedure. Okay. K counts the steps of the algorithm starting with 0. Okay, K equals 0. The next step corresponds to K equals 1 and so on. Okay. Each step begins with 2 non-negative remainders. Okay, yep, I'm gonna have RK less than RK1, multiples of the smaller number subtracted from the larger number until the remainder is smaller, and that is shown here. Until the remainder is smaller than the previous step before remainder. Remainder 2, remainder 1 are equal to A and B. The next step. K1. Oh, I see. This is A and this is B. And then we put them in here. No, this is the steps. Right? Yes. 0, 1, 2, 3. Okay. Oh my god. This is melting my brain right now. remainders equal b, remainder r, b additional stuff, and so on. Okay, yes, and that's how we got this equation, which was GCD AB, GCD B, R sub 0, R sub 0, R1, all the way out. Yes. If A is smaller than B, the first step of the algorithm swaps the numbers. For example, A less than B, and the quotient Q sub 0 equals 0. The remainder R sub 0 is A. So then this would be 0, so R sub 0 has to equal A. One quotient of 0. Quotient sub 0 is 0. Q sub 0 is 0. Okay. Okay, eventually R sub n will equal 0 and the algorithm will stop. Okay. And the final non-zero number is the greatest common divisor of each one, which would be like 1. Maybe. Okay. So here, first find Q sub 0, which is equal to 2 in this case. Then multiples of 147 are subtracted from 462 till the remainder is less than 147. So first it's 2, and then we would be left with 147. So is that R sub 0 then? Yes. And then we take the B, right, and we put it in the place that the A was. So this one would then be 1071 as equal to 2 times 462 plus 147, because this is A. This is Q sub 0, this is B, and this is R sub 0. Okay, it's finally starting to click. How long was that? Like 20 minutes? Okay, and now the next one would be B comes out here, and it's 462. And so we need to find the quotient over here again. And here it's saying 3. So we take the remainder. Okay, so then B is 1 times 147, because B this time is R sub 0. And we just kind of keep moving them along as we add new R1. And QO here they're saying 3. R sub 1 would be 21. And then we move again and we say 147 is equal to, because this is R sub 0, times 21, which is R sub 1, plus whatever R sub 2 is going to be. So 21 goes into 147 7 times. And then R2 is 0. So eventually we have to get it to 0. Once it reaches 0, then it's done. We don't need to tell it to end. It will end when it hits 0, right? I think so. Okay. And then last remainder 0, the algorithm ends with 21 as the greatest common divisor. Okay. So first you solve the equation, quotient, and then you have a remainder. Then you move the remainder in, quotient, remainder, remove the remainder in until the remainder is 0. Okay. Okay. Now how do we say that in code? This isn't quite right because it doesn't go through all of the steps necessarily. I don't have like let's see. So what do we want it to do? What do we want it to do? Let's see if we can figure out how to write this in code. First, what do we want it to do? And we'll see if we can make it neater from there. So first we want to take A equal to some number, but to get that number, so we have Q equals to A divided by B. If we do modulo, does that give us the remainder that we need? Let's look inside here. Let's get a new one. Can I just put input 1071 modulo 462? Let's see what I get. Okay, so that's going to put out the remainder, and then every time what I need to do take and what do I need to do? So R sub 0 is going to equal A modulo B. And then what are we doing? Then what do we do next? Then R sub 0 becomes B, which is this statement here. B R sub 0. How do we get it to move through that range, maybe? Because that will always give us the remainder, then we just need to move through. So first, A divided by B would give me the remainder of 147. Then, which is R sub 0. Then we want B, which was the 462 divided by the R sub 0. The remainder of that, so using the modulo. And then that gets us closer and closer again. That's the stuff we need to do over and over again. So we first take, it's just like this, A, then B, R sub 0, like I wrote here. Juicy. right? It's these steps. How do I tell it to go through this? I guess until remainder is greater than 0. I mean, we know if B is 0, return A. Okay, we've got that case. What are we going to return if it's not? Why, Felicia's? What do we return? What do we do? 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 Okay. We need to reduce B A is only used that initial time. It's like everything shifts. How do we shift it? A modulo B, then B modulo of the step before. Okay, that's how we're going to recursion it. So it's A modulo B first, and then let's see. A modulo B, right? And then we want to do B modulo that result, right? Yes. I mean, it's not B minus 1. It's A modulo B. I've almost got it. I want to say it's like, it's not times, it's like A modulo B modulo GCD AB or something like that. Right? Because we tell it to run the A divided by B, and we return the results of modulo. We don't want to return it unless it's equal to 0. A modulo B, that gets us the second step. So close. let's try this first. Oh my god. I guess I was trying too hard. Surprise. Oh, Fibonacci sequences. So it was just return G, C, D, B, A modulo B. Okay. How long is this? Okay, we can watch this. We have time.
We just saw an example where we could have multiple recursive calls inside the body of a function perfectly fine. I want to show you a different example now in which we could have multiple base cases inside of a problem. And for this, I'm going to use another classical problem called Fibonacci numbers. And here's the story behind Fibonacci. Leonardo of Pisa, also known as Fibonacci, posed the following challenge. He said, imagine I put a newborn pair of rabbits, one female, one male, in a pen or an enclosure. And I'm going to assume that rabbits mate at age 1 month, and that rabbits have a 1 month gestation period. That is, they produce a new pair. The female produces a new pair at the end of a month. He's also going to assume that rabbits never die, and that the female always produces one new pair, one male and one female, every month from its 2nd month on. And Fibonacci wanted to know how many female rabbits are there at the end of 1 year. So let's do a little sort of simulation of this, and then we'll figure out how to actually solve it. So we start off with a pair of immature rabbits, a male and a female, the 1st month. At the end of 1 month, they've matured. They can therefore mate, and at the end of the next month, they're still around, but they've produced offspring, another male and a female. At the end of the next month, the original pair have produced another pair of offspring, and the first pair of offspring have matured. And that means at the end of the next month, both sets of mature rabbits now produce offspring, and another one is matured. And that keeps happening as we start generating more rabbits and more rabbits and more rabbits until we're overrun with rabbits. Question is, could I model this to deduce how many female rabbits are there at the end of a year, 2 years, 5 years, and when will Australia completely get overwhelmed with rabbits, just to take an example of a place with too many rabbits. So, what does this say? I've got a little sequence here. In fact, they're known as the Fibonacci numbers, in which I have the following property. At the end of 1 month, I've got one female. At the end of the 2nd month, I've also got one female, who's now pregnant. At the end of the 3rd month, I got 2 females, one pregnant, one not. And in general, at n months, I've got however many females there were at the previous time, and I've also got however many females there were 2 months ago. Why? Because every female alive at month n-2 will have produced one new female at time in month n, and those can be added to the number that were alive in month n-1 to get the total that were alive in month n. So there's basically the definition of Fibonacci numbers. And how do I capture that in code? Well, here I've got 2 base cases. I've got how many females at time 0, how many females at time 1, and my recursive case, notice, involves 2 invocations.
Okay, hold on. So we have Fibonacci sequence. Okay. These cases. Still 1. Okay. And then recursive case. Is
of that function. 1 for n-1 and 1 for n-2. And if I want to turn that into code, there it is. I've got 2 base cases.
okay, and what it would look like exactly. Let's write that down. Because syntax is something I always struggle with.
I'm doing it in one test, but I'm saying if x is either equal to 0 or x is equal to 1, return 1. Otherwise, return fib of x minus 1 plus fib of x minus 2. And if I were to run that, I can see that I can actually compute Fibonacci. Given fib, I can check that my base cases work. Fib of 0 gives me 1. Fib of 1 gives me 1. And just to do a couple of trials, fib of 2 should give me the sum of those. And fib of 3 should give me the sum of those. And fib of 4 should give me the sum of those. And you can see, in fact, it is doing what I expected it would do. Here's a case where I've got two base cases. And in fact, I kind of know I need it because my return here in the general case needs two different invocations of that function. And I need two base cases to make sure that I can settle that out.
Okay. Next. I should be able to get through this one too, and then it's time for me to go.
We've seen a number of examples of recursive functions, something you're going to use a lot. But all of them so far have just been numerical. So let me show you one more example that I can do recursive problem-solving recursive functions on other things. For example, on strings. So here's the challenge. How would I tell if a string of characters is a palindrome, meaning that it reads the same forwards and backwards? Now I'm going to cheat a little bit and remove punctuation and capitalization, but I just want to know, is something a palindrome? Probably one of the most famous, attributed to Napoleon, although I don't know that he said it in English, was able was I, ere I saw Elba. If you look at it frontwards or backwards, it reads out exactly the same. Second one, attributed to Anne Michaels. Are we not drawn onward? We few, drawn onward to a new era. And you can see if I read it from right to left or left to right, it's exactly the same. I'd like to write a piece of code that can solve this recursively. And you can think about doing it iteratively, but recursive is so much better a solution to use. So how would I do it? Well, I'm going to do a little bit of cleanup first. I'm going to convert the string to just the characters. I'm going to strip out any punctuation, and I'm going to convert lowercase, or everything from uppercase down to lowercase. So I just have it all as a sequence of characters. And then I've got a very simple solution. If the string is empty, it's a palindrome. If it's just of length 1, it's a palindrome. Otherwise, how would I tell if some string is a palindrome? Well, check the first and last element. If they're the same, then check everything in between to see if it's a palindrome. That's cool. That's a recursive solution. I've just broken it into a simpler version of the same problem. And of course, as I keep breaking it down, eventually I'm going to get down to either a string of 0, if the whole thing started off as odd, or sorry, even, or a string of 1, if the whole thing started off with an odd length. Can I do that? You bet. I'm simply going to write a little. That's a recursive solution.
Characters. Stripping out punctuation. And converting uppercase to lowercase. Then base case. String when equals 0 or equals 1 is a palindrome. And the recursive case is make this bigger. Excuse me. If the first character matches last character, then is a palindrome if middle section is a palindrome. Okay.
I've just broken it into a simpler version of the same problem. And of course, as I keep breaking it down, eventually I'm going to get down to either a string of 0, if the whole thing started off as odd, or sorry, even, or a string of 1, if the whole thing started off with an odd length. Can I do that? You bet. I'm simply going to write a little piece of code that's going to say, if I've got a piece of code that's called is it palindrome, I'll first convert this just into the string. I strip out all the separation spaces, the punctuation, I remove uppercase to lowercase. And then, as I said, if the first and last element are the same, then I just want to check, is that a palindrome? And there's the code, nice and compact.
This one, I guess. For C, S, C, in lowercase alphabet. Answer equals answer plus C. Turn answer. And then we'll have another define is.
I got it.
Else return this index 0. This one. And is this one x. And then at the very end, we return is tab 2. Okay.
Nice and simple. I'm not going to walk through all of it, but you can see the first part here is simply something that's going to convert that string into characters. It takes advantage of a property of strings that I can call a method called lower that will convert everything into lowercase. And then I've just got a nice little iterative loop here that basically walks through each character in the string. There's that iteration over the string itself. It's a string iteration. And it basically says if that character is, in fact, a character, add it in. And then there's that nice, elegant solution to palindromes. It says, given one of those strings, if it's of length 0 or less, sorry, if it's of length 1 or less, it is a palindrome, return true. Otherwise, check the first and last. There's that call with -1 to the string, the first and last character of the string. And check by slicing out from the string everything but the first and last character to see if that's true. And finally, I'll just convert the string and call is pal on it. Let's try it out. I've got those two characterizations over here. I've got it loaded up, and if I call it, it says, is, for example, a simple thing like Eve a palindrome? You bet. EVE is a palindrome. And what about is able, was I, ere I saw Elba a palindrome? You bet. Again, notice how thinking about it recursively has let me find a really nice solution to this problem. This is a very, is able, was I, ere I saw Elba a palindrome?
Ah, okay, here's the prints. Okay.
You bet. Again, notice how thinking about it recursively has let me find a really nice solution to this problem. This is a very crisp piece of code that solves what otherwise seems like a very hard problem. Could you solve it iteratively? Sure. But you'd have to keep track of where you are on both ends of the palindrome as you decrement them to walk in. That sounds like a pain. I'd much rather think of this recursively, and that's what I did. This is, as to all the previous examples, but this is a really nice example of what we call a divide and conquer algorithm. I solve a hard problem by breaking it into a set of other subproblems that have the property that they're easier to solve than the original, in this case it is shorter, and that the solution of the subproblem can be combined to solve the original problem. We saw that with factorial, we saw it with other ones. This is a great example of it. And we're going to come back to this idea of divide and conquer algorithms as we go through the course, because they're a very powerful pattern that we want to be able to use.
Okay, that's me for today. We will pick it up some other time, maybe tomorrow, who knows. I'd like it to be, but you know, life. All right, bye.